Hello, my friends. We are back with more nuclear reactions here. So Monday and Tuesday, we talked about natural decay reactions, where one radioactive isotope releases a particle and produces another isotope. Today, we're going to start talking about artificial. And that's going to bring us, for the last couple of assignments for the year, that's going to bring us into a little bit more, I guess, research and another look into, or a deeper look into the uses of radiation. So you'll hopefully learn about a couple interesting things with that. So what I have here, I mentioned this on Tuesday, these are the answers to the 4 reactions that I mentioned that were natural decay on page 2 of the worksheet packet. What I'm going to do, because I'm going to go through some more of these with the artificial, I'm going to post a picture of this for you tomorrow, so that way you can finish this up, or actually I'll probably just post it today, but it'll be posted either with Thursday or Friday. Just check for an answer key for this so you can see what's going on. I will do a couple of these with you, because I want you to see that the artificial transmutation is exactly the same as the natural decay when you're trying to figure out that unknown radioisotope. All right, so on the bottom here, this is an important idea. This is how you differentiate between natural and artificial radioactive reactions. Natural decay, we said it just naturally happens. These are radioactive isotopes that could be found in a rock. They could be found in porcelain. They could be found, in the walls of your house, depending on what they're made up of. So these are elements that just are a bit unstable on their own, and they're going to release or let go of a particle. So we can see for numbers 1, 2, 3, and 8, we started off with one radioisotope, and we released either that alpha, beta, or positron. In these 4 examples, we only had beta for numbers 1 and 8, and we had alpha decay for 2 and 3. Okay, so remember that alpha could be written as HE. You could have also put in that, that alpha symbol there. Perfectly fine. But everything on the top must be balanced. So a mass of 42 on the left and a total mass of 42 on the right. An atomic number or nuclear charge of 19 on the left and a total of a nuclear charge of 19 on the right. That's how you figure out what you're missing there. So that's natural decay, 1 reactant, 2 products. Artificial transmutation. Now they don't call it decay because it's not breaking down. What's happening with artificial is you're actually going to have more than 1 reactant. Okay, most often you're going to see 2 reactants for artificial decay. The reason it's artificial is because if you think about every single nucleus for every single atom that we've talked about, they are all positive. Okay, they are all positive. And if you take 2 things that are positive, they are going to want to repel. They don't want to go near each other. All right, so those positive nuclei push away from each other. There's a natural repulsion. So in an artificial reaction, these are reactions that have quite a bit of energy going into the reaction to push them together and make them react. Okay, so I'm going to just talk about a couple of these because you'll see in tomorrow's assignment with fission and fusion the difference between the 2. Number 4, I'm going to put a little star on the side over here. This is a fusion reaction. And fusion and fission are specific types of artificial reactions. Fusion is specifically the fusing of hydrogens and heliums. So when you see hydrogens and heliums as your reactants, that's fusion. So if we take a look at number 4, again, we're going to put together our masses here. So on the left side, I have a total mass of 4 because I have 1 plus 3. I only have 1 product, so that 1 product has to have a mass of 4. On the bottom, I have a nuclear charge of 1 and 1. Well, I put that together and I get a charge of 2. So on the right-hand side, I have a nuclear charge of 2. So if you remember, how do I figure out what that element is? We go to the periodic table. Helium has the atomic number 2, which is also the nuclear charge. So our product would be helium. Okay, so that is that. I'm going to skip a couple more of these because I want to jump down to number 9, which is our other specific type of artificial transmutation. The others are still artificial. They're just kind of, normal, everyday, run-of-the-mill artificial transmutations. But the fusion and the fission, those two have a little bit more importance to them. And like I said, in tomorrow's video, you'll see these in a little bit more detail. So with fission, we have a saying with this reaction, and we refer to it as fission is the division. Okay, fission is division. So what that means is we're going to take something, we're going to take a radioactive isotope and divide it. Okay, we're going to divide it. And the way we divide it is we take a neutron and we throw it right into it. So this is where, if you're not familiar with particle accelerators, these are huge machines that take these subatomic particles and speed them up using electromagnetic forces, and then they take them and slam them into other particles to try to get some type of reaction. Well, in a fission reaction, what happens is a neutron is used and they speed it up, and there might be some heat involved, there might be pressure involved, but what they'll do is they'll take it and throw it right into another substance. So now what is that other substance? Okay, well, I have to take a look at what I got. For the mass here, let's say for mass, I have 142, I have 91, and then I have 3 neutrons. Okay, don't forget when we do balancing, we always take into account those coefficients. So this would be 3. So let's say, of course, I don't have my calculator with me right now, so I'll erase this just to clean it up. I have 42 plus 91 plus another 3, so that would be 94. So I'm going to have 6, 236. And I'm just going to erase that just to keep this a little bit cleaner. All right, so we have a mass of 236. Oh, actually, no, I have to hold on one second. If this is a mass of 236, I already have a mass of 1. It's not going to be 236. It's going to be 235. Okay, so a mass of 235, because 235 plus 1 equals 236. And that's going to equal 142 plus 91 plus 3, 236 on the right. For my nuclear charges, I don't have to worry about the neutrons. They have a charge of 0. So when I add these two together, I get 56 plus 36 for a total of 92. And the element that has an atomic number of 92 is uranium. Uranium, you may be familiar with when you hear about issues with nuclear weapons. Uranium is the radioisotope of choice for this fission reaction. And this particular reaction is what is used in the atomic bomb. All right, so when you hear about countries stockpiling uranium, this is the reason why. All right, that's the danger behind it, because uranium is that element of choice for the fission reaction. So that uranium gets broken into 2 smaller radioactive isotopes and some neutrons. This particular reaction is also used in power plants right now because it's what they're able to do. People talk about the danger of power plants. The reason why the power plants are dangerous, you do get tons of energy. And we'll talk about that in a second. You get tons of energy, but these products are extremely dangerous. They are still very radioactive. And when those products are in a containment tank, And that containment tank structure is breached, is broken. This is very similar to what happened in Japan a couple years back. But the reason that it was so dangerous to be in that area was because those containment tanks cracked or fractured, and radioactive products were being leaked out into the environment. So that's part of the problem. So the energy, what happens with the energy? The nucleus, all positive stuff. There's a ton of energy holding those protons and neutrons together in the nucleus. That's all potential energy. By breaking that nucleus, you release all that energy. And you might think, oh, it's just one little atom. Well, think about if you have, a few grams of uranium, you have yourself a pretty significant explosive. So when you're dealing with this particular type of reaction, this is why it is so important in terms of, what are countries doing with nuclear weapons? What are countries doing with nuclear power plants? If we were able to get the fusion reaction done successfully, this would be a much safer energy. This is actually the energy, this is the reaction of how the sun actually produces energy. So you think about the sun, that's a good amount of energy. So this reaction obviously works as well. But hydrogen and helium are much safer for humans. We inhale it every day, every second. So if we were able to get some type of nuclear power plant that's run with fusion reactions, this would be a much safer option. All right. So that is your work for today with artificial reactions. Short and sweet. So what I want you to do is try the rest of these numbers 5, 6, 7, and 10. And like I said, I will post the answer key also on the side here in that last little space. You're putting down an N or an A for natural decay or artificial transmutation. Okay, and like I said, tomorrow you have the video on fusion and fission, and you can see the uses behind it. You have a couple questions to go into that, and then we'll wrap up with some other really good stuff next week. Okay, have a great day, everybody. See you soon.